So we're going to get started with class in just a minute or two. If anybody didn't receive a copy of my welcome email, and I sent another link to this to our Google Drive that we're using temporarily for data sharing, please, before you leave anyways, I've got a sheet up here. Just put your name and email address on here so I can add you to my list. I still don't have access to rosters yet. So the snow day looks like that it might have pushed that back, so it could be another couple days before I get Husky CT actually set up. So we're going to keep using this system here. I have some other things active, but before you leave anyways, come up to the front of the desk and just write your name and email here. I will add you to my email list so I can send you stuff out if need be. Cool. But it looks like it is 9:30, so we can go ahead and get started. As I mentioned, still don't have access to Husky CT. I have some other tech that works. We also learned that some of the tech I was hoping still doesn't work. So one thing that we do have, I have my own computer here, which means that you guys probably just saw me start screen recording a video. So I am recording a video of this session. After class, I'm going to upload it to a private YouTube channel that I'll send you guys a link through both email, and I'll put a copy of it in this Google Drive here. Anyways, so you should have access to the lecture afterwards. As always, I'll post my slides too if that's the format you prefer, but with some topics, especially basic chemistry like today, there's going to be people at a variety of different levels of expertise at walking into this class. That's kind of to be expected when we're drawing on material from other classes that may have happened a little while ago for you guys. Well, some people may want to go back and rewatch the lecture a couple times. This is kind of a good study tool for exam. So I'll make sure you have access to that. Always try to take good complete notes in class anyways. There's always a chance that my screen recording might fail or something along those lines. But most classes, I'd say 90% of classes end up being able to be uploaded at least, so you should get extra study material. The other new thing that's in that drive, I put an updated copy of the syllabus that has this schedule on it. I did try to make sure that we didn't have an exam right before or right after spring break. So the schedules are always subject to change as we get behind or ahead, probably not ahead in a class like this. But this is probably, this should be the dates on exams, this should be the chapters in your textbook that I'm asking you guys to read. The one or two other notes, hopefully you guys saw this. Let me actually just kind of go out of here. If you went over to that drive that's shared with you guys, you see a couple different files in this. Well,
One of them, these were the alternate readings for today's class. So if you don't have the textbook, I know I've heard from several people that they are waiting for textbooks or mastering or stuff like that from Amazon. Well, I'm going to keep posting links from OpenStax for as many weeks as we really need with this. Once you get your actual textbook in, you should probably go back and reread those sections as well, but OpenStax is not a bad textbook either, so this should help you prepare for class. One of the other things that was in there, well, in addition to the syllabus and the slides from yesterday's class, I'll put the slides from today's class up once we're done, was this link for how to register for Mastering Biology. That takes you to this document here. I put the important too long didn't read section up top, which is make sure you have the 10th version of Mastering Biology. Mastering Biology is the homework package that we're using for this class. It's also a wonderful exam study resource because you can go back over this, you get lots of new questions. Answering questions is probably the best way to study for almost any exam. So this will be valuable to you. It's also, over the course of the semester, your homework is counted the equivalent to one exam, basically over the whole thing. So you'll get credit for submitting this. You can register for that in a couple different ways. So if you bought a textbook from the bookstore here, I believe it came bundled with Mastering Bio. So you should be able to use the access code from that in order to get in. The bookstore here was selling the 10th edition. That's what they had me listed for when I started here yesterday, on Tuesday. So that's part one. If you wanted to save money and you went off campus to buy old versions of this textbook, I can't recommend doing this, but I have been told that there are free electronic versions of it floating around as well. Any of that stuff's probably fine in order to serve as a resource to support your learning. It comes down to, do you prefer a physical copy of a reference or an electronic copy? Personally, I prefer an electronic one. But any of those are fine in terms of supporting the class. You can also go with pretty old editions too. I don't think a whole lot's changed in this one since the 8th edition. So if you've got old stuff lying around, that's great. You can use it as a support, but you still need the 10th edition of Mastering Bio. Fortunately, they sell that independently. This link should take you to a site here which will let you register for your course ID. If you don't have an access code already, there will be an option to purchase one. You can use PayPal or a credit card. I've talked to the bookstore here as well. They should be getting access codes in as well. They don't know when they will get them, but that's another option if you haven't bought one either. They also haven't told me a price yet, so I'm a little leery of that. But Pearson's site seems to be pretty price competitive with Amazon. I think it's like $3 or $4 more expensive, but you get immediate access to this. Said, I know some people who have ordered from Amazon have a pretty significant wait time for what's essentially going to be a printout of an access code. If that happens, you can send me an email with kind of your shipping order, expected shipping date, and I'll just make sure that I give you extensions in Pearson. But you want to keep up with the readings as well as you can so that you're still prepared for class. The extensions I'll give you will basically be, you'll have a week from when you get your mastering access to when all the assignments will be due. I also am definitely planning on the first couple Pearson mastering assignments being for practice. I want you guys to learn the system, and I want you guys to learn about how to use the hints, when to use the hints, because you get penalized for using the hints by grade. So I want you guys to learn and become a little bit familiar with the system before I'll actually end up pulling the grades from that. So eventually, once I get Husky CT and your grade book set up, the grade in Husky CT will reflect your performance. I need to figure out if I can actually set the early assignments in Pearson to be 0 credit or not on Pearson's site. So there might be some slight discrepancies in your grades, but that would only be because I won't be counting the very earliest lessons for credit. But you should do them to practice when you can. So that was this stuff. As I told you guys last class, I wanted to start out with a little bit of an opportunity for you guys to go in and ask me some questions about the syllabus. So this was the last slide we didn't get to in class. If there are some big things that I care about here, it's that I want you guys to be able to think about biology at the intersection of biology and chemistry. That's going to be a lot of the first exam that we're doing here. I want you guys to be able to reason scientifically. Your lab's really going to support this as well. So this would kind of be a bundle of things that are like using quantitative reasoning, using critical thinking, or your ability to do these things. We'll be working on a series of activities over the course of the year. Well, those activities will kind of help scaffold your process of how to learn to think about science. Your labs will do the same thing. So when you approach an exam, there's going to be a couple problems on there, not all of them, but a couple problems that I'll give you most of the information that you would need to solve it, but you're going to need to apply some of that in order to diagnose someone or figure out what the next step to do for a patient would be. You'll see a couple of those types of activities as we prepare for the second exam. I don't know if I have a whole lot of that for the first one. But that will be a component of the exam. It won't be a majority of the exam, but they are learning objectives, so there will be a couple questions on each of these. Maybe 10 to 20% of the credit on the exam will be for things that I'm testing your ability to apply and use items. It is this course is partially a language course as well. Anytime we talk about introductory biology or introductory chemistry or any of these sciences, there's a language behind it. You'll get a lot of terminology and vocab, especially today and especially in the early units. This stuff is foundational. And this is one of the main reasons why I want you guys to have and use the mastering program, because mastering is going to be a great tool to get a lot of questions, to test your ability, and to be able to become competent at practicing using the language of biology. And that's really how you're going to get great at this, and how you're going to get A's on the exams is by practicing. So we'll do a lot of practicing out of class. We'll do some practicing in class as well. I also want you guys to do some teamwork and communicate. I don't have the activities clearly defined yet, but I think a little bit closer towards the end of class, what I'll probably have you guys do is work in some groups to either diagnose or predict some cases of patients who might have a genetic disease and present that back out to the class. This wouldn't be for a huge portion of the grade, but I think that communicating science is a valuable skill, and it helps me get an actual point. It helps you or peers get an actual point where we can kind of learn a little bit more, or we can help give some direct feedback about how we do this. So again, that would probably be a very small percentage of the actual grade, but it's something that you might want to start thinking about. Most of us will eventually need to be doing some type of communication throughout our life, and definitely we'll be doing some teamwork in this class. I started you guys out, I think, on Tuesday, working with some of that. You can expect to, when we have activities in here, if I'm ever having you guys submit something for credit, you'll probably submit it as part of a group, because that will let me actually provide feedback on these instead of getting 200 assignments in that I'm not able to really effectively give you guys feedback on. So this is the last stuff we didn't hit about the syllabus. What I'd like you guys to do now, think, then talk to whoever's right next to you or right around you about any questions that you might still have. This is a type of active learning exercise. It's a think, pair, share. I find that people are more willing to share out in class if you've had an opportunity to discuss it with somebody else. So reflect on any questions you might still have, talk to whoever's next to you, and maybe that will give you the, or help make you feel comfortable enough to actually ask it in front of all of us. So take a couple minutes for that, then I'll definitely give at least 5 minutes for answering syllabus type questions.
Can I get a syllabus, please?
I don't have physical copies, but they are on this tiny URL here. So if you go here, because I still don't have access to Husky CT or any other resources.
You don't, or you do?
I do not yet. I will, but I'm a brand new professor here. I've taught for years anyways, but I'm new to Connecticut, so I'm not in any of their systems here.
All right.
So
I just signed up for this class. I wasn't here on Tuesday.
That's okay. I've got the slides from last class, and most of what we were doing was going over the syllabus. Before you leave, make sure you give me your name and email on this. Then I'll forward all early communication back onto you and everybody else who's new. You're welcome. Oh, sorry. Here you go.
Good, thank you.
And the email I'll send you will have a physical copy of this as well. So, or we'll have an electronic thing that actually you can click on, so that way you don't have to type it in. Cool. Cool. Thank you, guys. So as a reminder from last time, whenever you see me raise my hand, please raise yours and then stop talking. That will get everybody's attention and will stop me from having to yell over people. I don't want to be perceived as threatening. So let's go into the, or let's, now that you've thought and you've paired, let's go out and share. So what are some questions you guys still have? What can I answer? What can we address here? Nothing. I wrote a perfect syllabus and there are no questions. That's not true. I still have questions about how the class is going to run. Okay, how about I start us with one. What are the exams going to be like? Who wants to know that? Right, we probably have a good number of people who want to know what the exams are going to be like. So with any larger class like this, there needs to be a component that's going to be auto-graded. I don't have the time, no professor has the time to answer that much auto-graded stuff, but I really value getting your open-ended responses as well. So the exams will be a mix of credit, probably 60% of this might be multiple choice, 40% of it, again, kind of pulling numbers out of the air, but this is how my exams have broken down over the years, is a portion of multiple choice, a slightly smaller portion of open response answers. So that's not saying 40% of the questions, but probably 40% of the credit would come from a place where you have the ability to talk a little bit more about your reasoning. I find that to be really helpful. My students generally get a higher score on the open response than multiple choice. I also try to be responsive to my to the expectations. I try to set reasonable expectations going into the exam. So while I do not curve exams, I add some other things in here. I go back after the fact and I take a look at my questions, and if the whole class got a question wrong, that tells me something. That tells me that maybe we didn't quite get to in class what I wanted to. So I'm not going to hold you guys responsible for it at that point. There might be some creative ways that I give you guys credit. I might have you guys do an exam wrapper problem. I just had one of my other classes do this, where after the exam there were 2 problems that most people didn't get right. So what I did is I gave my students a chance to take those home after the exam, write kind of a response of why they thought the original thing was right and what they've learned now that changed their opinion. So I might find some creative ways to help you guys get extra credit on these if I've noticed a specific deficiency. I don't necessarily have extra credit assignments just because somebody wants additional credit, but if we identify that some of the standards we held weren't makeable, absolutely I'm going to alter those standards. I'm going to find a way to make sure that we're getting you guys to a point where you can succeed in this class. We do also have to be cognizant, though, that you're leaving this class and you need to be leaving it at a level equal. My hope is going to be at a level greater than your peers who are taking this at stores, your peers who've taken this at other locations. So the expectations for the exams are a little bit set from them, but if I didn't scaffold you guys appropriately, if there are some things we didn't quite get to in the exams, I'll give you an additional point to learn that, and hopefully that will help you guys succeed. Exams will happen in class. I have the dates posted on your syllabus, so there is an updated copy of the syllabus in there. I really tried to make sure that there's no exam right around spring break. So hopefully that gives you guys a full week to come back and prepare before you guys have to go into an exam. Cool. What about some other questions? What else do we have? Yeah. I normally don't answer bonus questions, but as I was mentioning, after the fact, if there's stuff that people get all wrong, I'll give you guys an extra chance. Classes work with 100% credit. I don't believe in giving extra credit on top of that 100%, but I am going to give everybody a good chance at getting that full 100%. Yeah, there won't be extra credit opportunities for the whole class. That's not really something that you can really do in college effectively. But again, if I see that the class is behind, if I see that the class missed an objective, if I see that many people in the class missed an objective, I'll generally give you an opportunity to go back and relearn. I tend to try to set my grading up so that I'm evaluating as much as I can once you've already learned something. And I'll give people multiple chances to get there if they really need to. So no whole extra credit assignment, but we do have some other things like having the mastering biology assignments. So if you take a look at the breakdown of grades, you're getting 100, so 1/6 of the credit of this course is coming from participation or homework stuff, so I think that should help boost some grades. Labs as well, you need to try, but you're going to be rewarded for your effort in lab as well. So I think that will all help us boost grades anyways. Yeah, And I think, oh, also, for anybody who hadn't noticed and dug through this already, let me actually go to the doc.can here. And I don't have this in the slide anyways. There we go. So if you notice on that last line, it's actually some glare on it on the top screen, but that last exam, the final exam, it's going to be fully cumulative. So stuff from any of the exams could pop up on that one, including knowledge-based questions and that kind of stuff. But if you do better on that final exam than any of your earlier exams, it's going to replace that one. So that, I would say, is closer to the bonus part of this. If you demonstrate to me at the end of the class that you improved and you learned, I want to reward you for that. So hopefully that's a structure that will help us succeed anyways. Zoom out of here. Okay, there we go. What else can I answer?
How would you grade that based off of
So the homeworks are going to go through Mastering Biology. They're auto-graded through that. It's one of the class this size, I wouldn't ordinarily be able to offer homework except through these packages that auto-grade them because there's not enough time with my teaching schedule in order to get through all of that. But it's also why you have to pay for these as well, is because you're paying for additional service that I can't render. But when you do that, this is going to give you feedback on those questions. If you get something wrong, it'll generally give you a couple extra ones that you can go through and do. You will get, well, I'll tell you right now about the mastering system. There are hints on the bottom. Try to do everything you can with the question before you use that hint, because I think when you use that hint, you are sacrificing credit in order to do that. So instead of using the hints on there, the first thing you want to do is read your textbook along with the problems. The homeworks are going to be aligned to each chapter. So only use that hint as a last scenario if you can't progress through something without getting any of the credit. And then you can use the hint and it will still give you most of the credit for that assignment. I don't know off the top of my head how much it takes off for this one, which is why at least the first couple homework assignments, I'm not going to apply the grade for these. I'm going to let you guys go through and learn the system and optimize your experience of how much do I want to use the hints versus my textbook before. And once you're comfortable using that, then we'll start collecting these for grades. That's not collecting, it'll be auto-graded. Yeah.
Are you going to provide any study guides or past exams before our exams?
Okay. Sort of is the right answer here. So there's a couple things I tried. So I'm still relatively new at making whole exams by myself. I don't have years of back exams that I can just give you problems that I don't need to use again. So I may not have the volume of questions that some other professors do. What I do for all of my classes, so what I just did for my last winter one, I'll do again. I'll have a quiz before each of the major exams. Now this is going to go into probably this assignments category of the of your grade, which means you're going to get basically participation credit for it, but you'll get an opportunity to see what some of the questions look like before you go into this. If I have other old questions that I can give up that I'm not using, I will absolutely put that there. In terms of a study guide, every one of my class sections, I think the slide has them, should start out with some learning objectives as well. I will compile all of the learning objectives into a single list for you so that you guys have a list of what are the skills and things that you're supposed to know for the exam. And that's going to be your best study guide. Go through that and try to reflect and say, do I know how to do this? And if you don't, then go back and review more. So hopefully that'll help. Well, what else? Anything else you guys can think of? No. I am sure that more questions are going to pop up. As they do, let's go ahead. Oh, maybe let me just share one or two other things about the Mastering Bio. Once again, if you go into the drive, there are those instructions for how to sign up for it. You do need the 10th edition of this. The link that's in there should take you right there if you haven't purchased an access code yet. If you did purchase an access code and it's on its way, as long as it's for the 10th edition, you should be able to sign up for my course using the instructor course ID that is in that document. It was something like Audette 1107 or like Bio 1107 or something along those lines with this year. So you should be able to find all of that and register. Keep me informed if you don't yet have access to it so I can give you extensions.
You said that we could buy the access code from both the bookstore and from Pearson?
Yeah, so that link that I gave you, once you put the access code in, it should give you the option to purchase it directly through them. That would be an immediate purchase. I think it's a couple dollars more expensive than Amazon, but I believe Amazon's right now are backordered. They're not coming until the 30th. So it's probably beneficial to you guys to have this well before your first exam anyways. So you can use it as a study tool. And the first exam was going to be on February 1st. So I'd worry a little bit about not having it then. I think the physical bookstore here is also ordering them, but I don't know if those might be backordered. Even if all it really is going to be is a piece of paper with an access code on it. So it may just be easiest to get that through Pearson. If you buy it as a standalone, I think it's price comparable with everything else you're going to get. So I still don't have the clickers set up here because apparently there's not a base station here. So I will need to get one. So I'll start clickers the week after that. I also need to see what Husky CT has. In the past, I've done these as take-home quizzes. So I'm not 100% sure yet. That said, what I do know is that since I don't have a grading category that is 4 quizzes, they won't be worth a whole lot of credit. So it's not going to tank your average whether we do it in class or out of class. It'll mostly be like a couple points or something like that, in a category that has a lot of points that you'll be getting 100% on because they'll be in our in-class assignments. Yeah.
We have to cut open frogs.
That's actually the other thing I meant to mention at the beginning. I still don't have a whole lot of information about your lab because we had the snow day yesterday, and that canceled my meeting with your lab coordinator. I have a meeting this afternoon, so I'll be able to find out a lot more. I'm going to share another email. So again, if you're not on my email list, if you didn't get that last email from me, make sure your name ends up here by the end of class so I can share that stuff with you. I know labs do start next week. I know we don't need to cut into frogs next week because next week's lab we're going to be learning about the compound microscope, how to use it, and we're going to be taking a look at some basically pond scum and identifying some stuff in it. It'll be fun. I've done a similar lab with my students back in Delaware, and I love this one. It's fun. I do know that we are doing dissections, so that I think you need to be prepared for. It was right in there on the lab syllabus that they showed me. You'll get a lab syllabus when you go to your first lab anyways. But I don't 100% know yet what we're dissecting. Okay. Let's hold any more questions for after class so that we can actually get through some of the material anyways. But I want to be responsive with this. If stuff comes up, I'll let you know. As we go through this, there's going to be a couple, we still don't have a way to do audience response because, as we're learning, my Poll Everywhere account is only running for my old class right now, which they had to pay to register, and I'm not asking you guys to pay for something else. So, starting next class, if we still don't have access to clickers, I'll create one of these things that you can do anonymous submissions on near term. But for today, we're going to have to go old school and just do hand raising. So hopefully you're okay with that. Today's lesson, we're going to focus on sort of the chemical basis of life. We're going to start with carbon and water. These are, oh, and as a quick reminder, you're getting slides. You're also getting the video lecture here. So if you're ever behind me, you can go back and re-listen to the lectures. You can go back and get more. So take enough notes. Take notes that will help you focus in class, but don't just write things down without trying to understand them, I guess. You'll get more time. So today's lesson will be on carbon and water. We're going to focus on a couple different things. These are kind of our learning objectives for the first class. Later on, you're going to get more specific learning objectives from me, but for right now, I think this is what I have for you. We're going to learn a little bit about the structures of atoms, how they form molecules, and how those are bonded together. And we're definitely going to focus a bit on the unique properties of water. We're going to dig through that for most of this class. Next class that we go into, we're going to think a little bit more about reactions. We're going to think a little bit more about larger molecules and macromolecules and how the structures of these things support the biological structures of life. That's kind of the big picture. That's what we're doing in the next couple weeks. At its most basic point, and I'm also going to try to go in here and pick out some things that would be good to know or not know, or things that would be good to know or things that you don't need to worry about studying. Life on the Earth is made up, or 96% of life on Earth, or 96% of the things that make up life on Earth are going to be hydrogen, carbon, nitrogen, oxygen. I don't need you to know that number. I don't need you guys to know names. Those are not things that will be required on the exam. What's probably important, though, is to gain a good working understanding of how hydrogen, carbon, nitrogen, and oxygen interact with each other. And that's what we're really going to be digging into today. We'll start with kind of the physical structures of these, how they're a little bit different. That's going to come down to valence shells or not. We'll get there. And we're also going to take a look at the structures of simple molecules. Specifically, we'll take a look at water. I don't think we'll get into carbon dioxide yet today. That's a pretty cool exception to the rule, but we'll be looking at water. We'll be looking at salts, so NaCl. We'll be taking a look at ethane and then some larger hydrocarbons and kind of learning about how these things interact and how they mix. If you mix these things together, does it form a solution? Does it form a mixture? Does one thing precipitate out or not? We'll get to all of the terminology for that in just a moment. So, at its basic level, we start with the atom. The atom's made up of a couple different items. We have protons. These are a nuclear particle. These have a +1 charge. We have electrons. These are negatively charged. They have a -1 charge. We also have neutrons. These things give our atoms mass, but they're not a charged unit. They can help stabilize that core. This isn't a P-Chem course. We're not going to go any farther into it than that. Our protons are going to be located in the nucleus. Electrons are found in orbitals surrounding the nucleus. And one of the first things that we're going to be learning about is that orbitals can hold different amounts of electrons. So who here has heard of like s orbitals and p orbitals and that kind of stuff? Yeah, most of you guys have had chemistry at some time. That's a good start. We're also going to be starting thinking about energy. What things are favorable? So there's going to be a pull in a natural force sort of bringing things towards low energy standpoints. So if you were just kind of bleeding the heat out of a system, water's going to form ice, right, as it cools. Even oxygen, eventually, if you cooled it enough, would form a solid or liquid. So we're going to be working a lot in biology to think about things that are energetically favorable, energetically unfavorable. Our system, life, we're going to expend a lot of energy in order to sustain unfavorable reactions. That's one of the major tenets of life. And we're going to explore how some of that happens. But you could think that there's a whole bunch of things that need to be fulfilled in order for us to be here right now. I can tell you that for me, one of them is that I need caffeine. But more specifically, there's a bunch of sugar in here. So what's getting me through my first lecture and now this is because I'm intaking energy. That's a good start. I probably need to have the ambient temperature in this room be above freezing long term, right? So there's all of these different things. So if we start taking energy out of this system, life starts collapsing. That's going to be another big theme in the first 2 units that we're working on. But what we'll be doing is using energy to predict the interaction of some of the different chemicals that we're working with. We're not going to go through this one because we don't have a clicker. But if atoms have the same number of protons and electrons surrounding them, so let's start with hydrogen. Hydrogen has a single proton in its core, and it has a single electron orbiting it. We're working on a Bohr model, or somewhere around it. Is this thing charged, or is that thing neutral as a whole? I think it's neutral, right? It has one proton, so this is a +1 charge, +1, -1. So at its most basic at its most basic point, this is going to be a neutral atom anyways. That said, we're going to also consider helium. I'll draw this one a little bit smaller so we actually have room. So helium's got two protons. And it also has this orbital around it that has 2 electrons. Is this more stable than hydrogen? Let's have hands for, well, let's do 2 things. Is helium neutral? Yes. Is it charged? No. So it's neutral as well. Is helium, I'll say one of these things is more stable than the other. Who thinks that helium is more stable than hydrogen? Who thinks that hydrogen is more stable than helium? Okay. So helium's more stable. Does anyone want to tell us why? What does this come back to?
I think it's more stable, one because it's one of the lower gases, but the valence electron shell, it has sure how many electrons, but on the outer shell, it requires 8 and it has 4 valence electrons. Do that for just 8.
Great. So when you start taking a look at atoms, so these are really simple ones, right? Where we only have one shell. We're going to start dealing with this thing. So let's say, in term list, we'll say valence electrons. So these are the outermost electrons. If we had something like carbon, carbon's going to have an inner shell with 2. We have a couple different orbital levels that are accessible to most atoms. When you start dealing with molecules, that these get big and complex. But an atom's going to have an inner shell. So this is your s orbital. I don't need you guys to know that for this class. It's going to have an outer shell, which is going to be, these are going to be a variety of p orbitals. And in this one, it's going to have 4 orbiting this thing. Realistically, these things make a funky shape. You guys have probably seen these things look like weird structures, but right now we can kind of work with the simplified version of this. There are, with the exception of that first shell, which is filled with just 2, all other shells on top of that are filled with, or all other levels past that are going to be filled with 8. There are some subshells. We're not going to go into that within this class anyway. But what we can think about is this idea that something that has a filled shell of electrons. So if we take a look at this, who's seen a diagram that might look like S2P? Who's seen orbital filling diagrams like this? Is this something you guys did in chemistry? So each of these orbitals can hold 2 electrons. So if we have our lowest shell here, that's going to be hydrogen. So for hydrogen, we just have a single electron in our shell. If we go to helium, this is hydrogen. If you go to helium, you're going to have 2. So this is going to be completely filled. And if we go to carbon, right, we've got our s orbitals filled, and we've got 4 of these. So we'll actually end up putting one in each of these. So now we've got 4 half-filled things. So this would be, what we're kind of observing is this idea that it is more energetically favorable. So helium is more energetically favorable because it has filled orbitals. That's just kind of something that you might want to know. It's kind of a basic, if you understand that, you can kind of extrapolate some of the rest of chemistry from it. This idea that things are more favorable if they have filled orbitals, which means that if you had a way to bond a bunch of hydrogens, which have 1 electron, to these carbons and have them share electrons, they might be more stable as a compound that way, because more of them could fill similar shells. We'll get there in a moment. But are we okay here as a starting point anyway? So if we had, let's think about a couple of these things interacting together. So let's make our hydrogen a little smaller so we have some room to work. Well, let's say that you had a hydrogen here, electron around it, and there's another hydrogen. Again, it has a proton, it's got an electron around it. And these things are just kind of floating out as a gas, and they hit each other pretty fast. Do you think they might have the ability to stick together? What might end up happening is if these things hit, hydrogen 1 has an electron, hydrogen 2 has another electron. Both of them have an empty space in their 1s orbital. So what ends up happening is that these things can hit, and they end up forming a bond that is sharing. The bond is basically the process of sharing those 2 electrons. And bonds are a stable process. They exist because this thing is energetically favorable. What ends up happening is, okay, now we have 2 hydrogens that both have their 1s orbital. They've got an electron spinning each way. And that's kind of what a bond is. This is a covalent bond here. So let's also go with terminology. We'll go bond types. So let's say covalent. You are also going to have a bunch of stems and roots of words that will help you guys on an exam. If you don't know something, but you know, you can tease out parts of the word. I'll kind of help extract some of this for you guys. So co generally means together. and valence probably means valence. So these covalent bonds are going to be a sharing of valence electrons. That gives each of these partial access to one of those. And that's going to be where we're starting today. Once we start wrapping electronegativity in here, we'll see a couple other ways that atoms could interact with each other. But one of the most common ones that we're going to see in biology anyways are these covalent bonds. They're going to be the sharing of these things. Just a little bit of review from that. Protons had a plus one charge, electrons had a minus one charge. When they had equal numbers of protons, electrons, they were uncharged. So both of these have a plus charge here, negative charges in the middle somewhere. So these molecules are still neutral. There's no formal charge on them. But these things could interact together and form these bonds. This gives them a filled outer shell of electrons. Again, hydrogens were a specific case. Their outer shell of electrons just is filled with only having two of these things. So these things were able to bond and stick. If we had another helium here, got two positive charges. These things hit each other. Do you think they're going to stick together, or do you think they're going to bounce off each other? All right, hands for stick together. Hands for bounce off each other. Good. Now let's examine why. So if these things, you could probably put a huge amount of energy into this system and get them to bond together. But if these things bonded, what you would end up having, so we started out with helium with a completely filled electron shell. If you bonded two of these things together, we'll call this our next shell, right? If you bonded these two things together, they'd probably each have a filled shell here and access to two more, so they'd have not only completely empty shells, which is not stable at all, they would also only have half-filled orbitals. So again, a whole lot of stuff that's not favorable, which means that you'd have to put a ton of heat into this thing in order to make that happen, way more than we would be dealing with in biology. So don't really need to worry about that one happening. So your assumption then that these things are going to bounce off, I'd say is right. It's not going to be a nice stable interaction here. And when we start digging into the modeling, you'll kind of see this as magnetism, which I like. I think it's a good analogy for it. These things would be kind of electrostatically attracted to each other. They form these bonds, which are the sharings of electrons. These things, well, it's not favorable for them to form a bond because the next orbital level doesn't make sense for them, right? They end up being far less stable together than they would have been apart. That's going to be a lot of the fundamentals of chemistry for this. Questions about this part before we move on farther? Anything you guys can think of? No. All right, well, we're going to throw another big wrinkle into this then. Before we go farther into this is electronegativity. This is a topic that students tend to find challenging within biology. I really encourage you guys to take notes, but also go back and use this video again. You're going to get access to this. Read about this while in the textbook. Make sure you're answering problems to challenge your understanding of it, so that you can identify if you have a misconception with this part. If you can identify that early, it'll save you guys from missing credit on exams or quizzes or mastering bio. So this is another wrinkle. Another fundamental property of atoms is their ability to pull electrons towards themselves. This is just kind of a chart of it. The units that this is in isn't particularly important, but if we took a look at this, let's just make sure my pen's on. There we go. If we took a look at this, fluorine here has an ability of 4 to pull things towards it, whereas lithium here has an ability of 1. So if you were somehow able to bond to create lithium fluoride, well, the bonds would be, the fluorine would be pulling most of the electrons from lithium towards itself. And that's going to create kind of the two next types of bonds, and we're going to examine them. And this is going to be a bit of a spectrum. So we'll say polar covalent. Leave some room around each of these when you're writing them down, because we'll explore these as we're going on. Polar covalent or ionic. So if you have things bound together, and we're going to start with water as our first example. We have an oxygen. Oxygen is going to have an s orbital filled, right? And then it's going to have 6 valence electrons in that next shell. So we will have a total of 8 protons. 1, 2, 3, 4. So we'll have 2 in the s, and then that there. So we've got 2 empty valence electrons. Or sorry, we have 8 protons total. We've got a filled s shell. And that p shell around it, we've got 6 electrons in here, right? 5, 6. If this thing had access to 2 more electrons, it would be at 8. That's pretty stable right up. We go back over to our energy filling diagram here. We have a complete S shell, and we should honestly write this as 2s/2p. So there are 4 relatively equivalent shells that are available to this thing. Yeah, chemists might yell at me for simplifying that, but this is probably the easiest way to understand biology. Our oxygen, we had 6. So we start out by putting an electron in each of these. We have 2 more, so we'll kind of put them here and here. So oxygen still has 2 available slots for electrons before it gets to its octet. So if we took our hydrogens, and they're kind of floating around, and eventually a hydrogen comes in here, it has a single proton, and it has an electron available, hits this thing, well, it's going to form a bond, like we saw over there. And that gives our oxygen 1 more, and we'll do that again here. Water has 2 hydrogens. So let's have this electron being shared here. Here we go. So now oxygen has at least a shared part in 8 electrons in its valence shell. That's good for it, right? This is nice and energetically stable. So this is going to be a covalent bond. But the wrinkle we're going to throw onto this now is, what is the ability of either oxygen or hydrogen to pull on these electrons? So if we're just working with the numbers here, how hard can oxygen pull on an electron? What's our number for that? 3.5. 3.5, but we can all just kind of shout it out too when you get there. So oxygen here is going to be pulling on these electrons with a force of 3.5 electronegativity. What about hydrogen? How hard is hydrogen going to be able to pull this bond? 2.1. So not nearly as hard, right? So do you guys think the electrons then are going to be located closer to hydrogen or closer to oxygen? Oxygen, right? So we can never pinpoint exactly where an electron is going to be at a point in time, but if you kind of drew a probability here, they'd spend more of their time over near the oxygen than they would near the hydrogen. So if we do the same thing on the other side then, because oxygen's still pulling harder in that direction, this hydrogen, how many protons? This has 1 proton, right? It started out with 1 electron, but now it's sharing that electron with an oxygen, and that oxygen has that electron for a lot more time than the hydrogen has it. It's closer to the oxygen. So that hydrogen is no longer completely neutral, and that's going to be key here for our polar bonds. This hydrogen is going to be partially positive. So this is the symbol for delta anyways. It's one of the ways we represent this. You might also see people do these kind of arrow diagrams, but I'll generally put it this way. So positive. This oxygen has 8 protons, but it now has a majority share in 10 electrons. So this thing's going to be partially negative. Electrons are negative, it has more of them than protons. The oxygen itself will be partially negative. This thing will be partially positive as well. That's going to be critical. What do we think is going to happen if if a water molecule hits another water molecule? Might it be able to bond or at least have kind of a magnetic attraction with the other one? Maybe. Would the hydrogens have an attraction for each other? No. The oxygens wouldn't have an attraction for each other as well, right? The oxygens would be two negative terminals interacting. If you think about, if you put the two negative sides of a battery together, they're repelling. But if you put the partially positive side of water, so the hydrogen, towards the partially negative side, so let's go over here with the dot cam, towards the partially negative side, well, those things might attract, right? And you're going to see something like this. They're going to form these longer structures. If you notice that what's happening, we have our partially positive hydrogens here attracting to our partially negative oxygens. They're going to form a long structure. Now there's some randomness here. This isn't the strongest interaction in the world, so if you're in a liquid form, there's still some energy there. Well, you'll have some ability. Every now and then some of these things are going to split off and form a new one. And another one's going to come on here. And another one's going to split off and it's going to go over there. And that's what our water phase is going to look like. It will have a relatively finite volume, but it's going to kind of move around each other and slide around. So there's going to be some ability for these long chains to move around each other, and it's going to form a solid sort of, like there's a volume to liquid. It's not going to expand to fill the space that it's in. But if you put a bunch of water into a cup here, it's going to fill the bottom of it, right? That's one of these ways that these intermolecular forces are going to work. But we learned a couple important things here. Most specifically, we learned that our partially negatives and partial positives are interacting with each other. Now, there's another thing I want you guys to consider here. And there will be questions on this one, believe me. This is not the easiest topic to get through. But if we had a sodium and we had chlorine, so if we go back to our chart of electronegativity here, this sodium, we won't worry about the inner shells, but its outer valence shell is going to have a single electron if it's neutral. Chlorine, its outer valence shell is going to have 7 electrons. 2, 3. So let's just kind of say that these here are going to be a pair in an orbital. These two are going to be a pair in an orbital. These two are going to be a pair in an orbital. And here we have a single orbital filled outside the valence thing. We have a single one filled here as well. Well, this would be a whole lot more stable if these things could share that electron, right? Then, well, chlorine at least would be filled, right? That's a good start. So chlorine would be a lot stronger here. You're going to start hitting two other things. Sodium might be more stable if it lost that electron, but even if it wanted to keep it, how hard can sodium pull on an electron? So if we start bonding these two together, what's going to happen? How hard can sodium pull? 1 or less. Is it 0.9? Is that what it was? Yeah, 0.9. How hard can chlorine pull? 3. That's a really big difference. So this is going to come back to, there's basically a number that chemists have under most conditions. If we see a difference greater, let's write this fully. Difference in electronegativity greater than, say, 1.7 or 1.8. What we're actually going to see is that this chlorine is going to completely pull this electron from sodium. So we're not actually going to be forming a covalent bond with them. There's going to be no sharing of electrons. Chlorine's just going to steal them. So in an ionic bond, this is an ionic bond anyways, the more electronegative atom steals the electrons. Whereas a polar covalent bond, that's these that we saw here, we said that the more electronegative atom, well, it'll be partially negative. It'll have a little bit of a greater share in the electrons there. And then this is going to be the key difference, and what changes that is going to be the degree of difference between the two atoms in that bond. And this is the critical part that people start missing on exams, because people start memorizing oxygen as being a polar thing. Well, you want to go one level down past that and understand that it's really a difference in electronegativity. This thing's polar because the difference here, it's like 1.4. Well, that's not enough for oxygen to completely pull and remove that electron from hydrogen. But this difference between sodium and chlorine, well, that thing's just going to completely steal that electron, and now chlorine's going to have a filled octet, and sodium's going to be one short. So sodium here, that's going to have a full positive charge, right? That's going to have a +1 charge because it's actually missing an electron relative to the number of protons it has. Chlorine's going to have a full -1 charge. So these are formal charges. It means that it's a difference of a full electron or protons amount anyways. They're considerably stronger than the partial ones here. I'd say most partial charges, maybe it's about 1/10 as strong as this. But they still matter, and they're still going to affect how our system's going to interact here. So if we had, let's start out with this. So this is our table salt. So we've got sodium and chloride. Now if you have a full positive and a full negative charge, these things are going to be associated with each other most of the time, right? Something that's a negative is going to be sticking next to a positive, but if you put this in solution, you might be able to pull them apart, and that's what we're going to look at now. So if we start putting water in here, once I condense this, so once we take some of the energy out of here and we start moving the water into the liquid phase, what we want to start thinking about is what's going to interact with what. So water has this partially positive hydrogen. Is water going to interact with the positive sodium or the negative chlorine? I'm hearing some murmurs. Who thinks it's chlorine? Good. Most people are on track with us. So we've got, let's see anyway. So let's push this in. So, and we can also probably pick out which one's sodium and chlorine based on that. So if we kind of start doing that, all right. So we learned, well actually this one didn't attach right. The magnets are not a perfect analog. There, that works better. So what we just learned here is that we took this solid chunk of salt that we had. So this is like a grain of salt that you would take out of a salt shaker. It probably has a couple, well, it'd be considerably larger than this. That might be 1,000,000 molecules stacked together in this really rigid cube. Well, we learned that the partially negative oxygen here is attracted to the blue thing. So, what do we think the blue thing is? All right. So the blue, so this is partially negative. This is probably fully positive. So what's blue? Sodium, right? This is partially positive, which means that this thing is probably going to be negative. So chlorine. So right now we don't have enough stuff sticking to this in order to destabilize the interaction of the negative with the positive, right? But if we did this a bunch more times, I'm going to do chlorine because it's a little easier to stick these things on. So let's add one more. Let's add another one, oops, on top of this. Oop, that's the one that's not magnetic. Here we go. Let's add another one here. All right, so we're getting pretty close. We'll add one more. And let's just say we kind of randomly, we're close enough to the amount of energy that would be needed to pull this thing completely off. And add maybe one more. So we finally now have enough bonds between our partially positive hydrogens. These are maybe not full bonds, so they're not anything that's appeared on here. But we have enough interactions between our partially positive hydrogens and our negative chlorine to put this thing into solution. So let's add those terms as well, right? So we've got solute, solvent, And let's add solution here. So solution is going to be a, let's say, a perfect mixture of parts. So if you just kind of leave it sitting there, nothing's going to precipitate or fall out of that. Well, that solution is going to have two parts. The solvent's going to be the thing that's, there's going to be much more of this. And the solute's going to be the thing that there's much less of. So we can think about what we just did here. We had a pot of boiling water, and we threw a tablespoon of salt into it. So the salt, because there's much less of it, that's going to be our solute. Water is going to be our solvent. And we're trying to investigate what types of solutes would interact with different types of solvents. So water, is that going to be polar or nonpolar? What did we learn over here? Okay, who thinks water's polar? Good, we're on the same track. So water's a polar solvent. This salt, is that going to be charged, polar, or nonpolar? So who thinks it's going to be charged? Hands up high. Who thinks it's going to be charged? Who thinks it's going to be polar? Who thinks it's going to be nonpolar whatsoever? All right, well, we learned over here that our sodium has a +1 charge, our chlorine has a -1 charge. So this is a charged thing. Charged things are, we can probably add the terms hydrophilic and hydrophobic. Who's heard of those before? All right, good. So this is another one that we can probably start teasing out the definition of based on just naming, right? So we've got hydro, so that's going to mean water, and philic, or phobic, or hydrophilic or phobic. Philic means loving, or phobic, hating, or something like that. So hydrophilic is going to be interacts well with water. And phobic is going to be interacts poorly with water. You want to be comfortable with this terminology anyways. But our salt anyways, is this going to be hydrophilic? Hands raised. Is salt hydrophilic or is salt hydrophobic? Okay, most people said hydrophilic, you're right. It's going to be charged. Charged things tend to be able to interact with polar things. And as we just saw here, if we add enough water to this system, let's dump out some more anyways so that we've got this. We can add enough molecules of water to fully solvate or dissolve these things, right? We added more, we'd be able to get this other one too, but I don't have enough water hanging out around for us to be able to do that. So that's a little bit about how we've gotten so far. We've got solutions, solutes, solvents, we have things that are hydrophilic, hydrophobic. This is all great terminology for you guys to learn and to be able to think about how it would work. And we've studied a couple different types of bonds. These are our polar covalent ones. We've got our ionic bonds, so again, complete stealing of electrons versus unequal sharing of electrons. We're going to throw the other wrinkle here. Oop. Let's get out of my markup thing. We're going to throw another wrinkle in here and start thinking about what's going to happen if we have, go back here. We're still learning some of the tech here. We're going to throw another wrinkle in here and start thinking about what happens if we've got these guys. So these are hydrocarbons. We have hydrogen and carbon together. Let us do this one on the board anyways. So we had our differences in electronegativity. Carbon can pull with 2.5. Hydrogen can pull with 2.1. So if we've got, let's see, do I have a good place to draw this thing? Let's put it all the way over here. So if we have a carbon, it's going to have 2 electrons in its s orbital. Then its outer valence shell, it's going to have 4. How many more electrons does hydrogen want to have access to in order to become stable? Okay, I heard 4 muttered a couple times. It's good. It's the octet rule. It's going to want to have 8. That would allow it to have a full set of s and p orbitals in that second shell. Well, you could do that by bonding it to hydrogen, or by bonding it to 4 different hydrogens, right? So each of these hydrogens is going to have another electron, and we're going to share these here. Right? This is pretty good. It means that hydrogen is now going to have access to 2. So its configuration is going to be closer to the noble gas helium, which is nice and stable. It's got to fill that shell. Our carbon's going to have access to 8. So that means that it's going to be nice and stable. It will have a full octet as well. But let's think about the sharing here. How hard can hydrogen pull? 2.1, right? So we'll work with this top one. So we can pull 2.1 in this direction. How hard can carbon pull? Is it 2.5? Is that right? 2.5 in this direction. That's not a very big difference. Now, if you were a chemist, you might think that there's some difference there. There's going to be things that are less polar than this. But we're going to kind of split things off into being polar or non-polar. So I would say the threshold here, if we said that a difference in electronegativity greater than 1.7 is going to make something ionic, I'd say a difference in electronegativity less than 0.5 will make it nonpolar. That said, I'm not going to go on to an exam and ask you guys to pull these off with a specific question, but if I gave you this as a reference, it might just be kind of helpful for you guys to predict this if you ever forget that oxygen, carbon is a polar attraction, or oxygen, hydrogen polar together, whereas these are going to be nonpolar. The other place we're going to see this is if any things are bound to themselves. So yeah, let's work on another misconception here. If we had 2 oxygens, each of these oxygens has a full s orbital, right? And their outer valence shells, they have 2 sets. And then they have some lone pairs. They have some lone electrons. Well, if these things happen to interact with each other, they can form an octet by sharing these, right? So we'll have a bond here, we'll have a bond here. This is going to be a double bond. How hard can oxygen pull on an electron? 3.5, right? So this one's pulling 3.5 in that direction. What about the other one? It's going to pull 3.5 in the opposite direction. So even though oxygen is really electronegative, if it's bound to itself, or if it's bound to something else that's really electronegative as well, you'll have an equal sharing of electrons. So that thing's not going to be polar overall. I go over this because this can be a pretty big misconception on exams. People just kind of memorize oxygens and things that are polar. Well, it's not going to be polar if it's bound to something else that's just as electronegative or nearly as electronegative as itself. We have carbons here. You can draw this with carbon too. If carbon bound to another carbon, it's going to be pretty there's going to be next to no difference at all. So that would be non-polar. So let's make some predictions then about, I am going here. Let's make some predictions about what would happen if we took our water. So this again, we're going to throw stuff into our pot of boiling water here. What do you think would happen if we added, what do you think would happen if we added these hydrocarbons? So this is carbon and hydrogen bonded to each other. So we've got some carbon-carbon bonds. We have some carbon-hydrogen bonds. We learned over here that those are not polar. Not a really big difference in electronegative. And we throw them into a pot of this. So this is going to be water here. Right? So we've got big differences in electronegativity. We have some partial positive terminals and partial negatives. Do you guys expect water to be able to bond well to our hydrocarbons? A lot of shaking heads. So let's see what happens. We're going to set some of these up. What was that?
They just really like each other.
Oh yeah, they do. It is difficult to get these things apart. So let's drop these in and see what happens. Well, our waters are kind of bonding to each other, right? But nothing's sticking effectively to these. Now, where your hydrocarbons end up is going to depend a little bit on what container they're in. So let's say that we've got, actually I don't think these magnets are strong enough to pull this one off, but let's work with the salad dressing analogy. Salad dressing, at least a vinaigrette, is going to be a mixture of something pretty polar, so like a water-like vinegar, something like that, and something pretty non-polar. It's going to be oil. So if you made these things a bit longer, if you added 8 or 9 hydrocarbons in a row, you're going to end up with something that looks like cooking oil. Our vinegar in an oil and vinegar salad dressing is going to act a lot like these. Well, if you let that thing sit in your fridge for a half hour, what happens? Does it mix well? Or do you get distinct layers? Yeah, distinct layers, right? So what you're going to see, if your container has an open top, well, you're going to get a separation between them. The heavier one's going to go on the bottom, the lighter one's going to go on the top, and there's going to be there's going to be no mixing of them whatsoever. There's going to be a straight line. All the oil's going to sit on top of the water. Well, it's because all of the water will be interacting with itself and kind of pushing the oil up to the top of the container, like this. Now, if you shook that thing up, you can get this thing to mix a little bit. We do this before we add salad dressing to something because we don't want to just add a bunch of oil from the top of the container and then only have vinegar at the end. But if you did this, you could probably get it to break itself up a little bit, right? So you get some of the oil separated. But over time, these things will move around, and eventually the oil would end up condensing into pockets where you have more oil closer to itself, just because the oxygen, the water around it's going to be binding to itself and kind of excluding these things towards zones where just the oil are, and eventually maybe that will float up to the top of a surface or something along those lines. So we're going to see, we go back over to the laptop here, we're going to see a lot of stuff that looks like this. Zones of exclusion where all of our hydrocarbons are going to sit. And we're not going to dig too much farther into that today. This is going to be really important for how membranes in biological systems are going to be drawn together, but this is going to be kind of foundational for where things are organized within or outside of a cell. Quick review, this is some good stuff to know anyways. What's our big important stuff about water? Why is it so important? Well, one of the things is that it's small, right? Polarity is kind of a scale. Well, 100% of the bonds in water are polar, and they're very polar. And because they're bent, there's a net dipole on that molecule. That means that these things are all kind of pushing towards the oxygen. We're going to have one side of this oxygen that's really, really partially negative charged, and then the hydrogen is going to be really partially positive charged. That just helps this thing interact with other polar items. So water's going to be about as polar of a solvent as you can get. That means that it's going to be really effective at dissolving things that are even just partially polar. So if we went over here, and I took one of, that one here, I took one of my hydrocarbons and I added an alcohol group to it. So this is methanol. Don't drink this one. But I put that in here. Well, all of a sudden, while this thing here can't interact, this thing can a little bit. So some things that are, as a molecule, slightly less polar than water, but still have some polarity, those things are going to be able to dissolve in water. Beer's a great example of that. If you let beer sit for a while, you're not going to get 2 layers. You're not going to get an alcohol layer and a water layer, because it will form a solution with water as the solvent and ethanol as the solute, assuming that the water greatly outnumbers the ethanol molecules in there. That would probably change if you were working with grain alcohol, right? If you had something that was 95% ethanol and 5% water, suddenly the alcohol would be the solvent. but it's still polar, so that still makes a pretty decent layer that you'd work with. So we're kind of learning a little bit about how molecules would interact with each other. And these polar molecules are going to be pretty important. We're going to keep exploring them. Good. So the last thing we really didn't touch on yet that I'm going to leave you guys with, we've just got a couple minutes left, is going to be the importance of carbon to these molecules. So we dealt a lot with water. This is why we care about water, and if we're ever looking for life on another planet, we're going to be looking to see if water is there, because water is this great, amazing solute. It's really difficult to get anything interesting to happen if you don't have water there. But carbon's pretty cool too. We dealt with the fact that it has 4 valence electrons over here. That means that it could bond 4 different things. That's really rare. Most chemical combinations that are inorganic or basically non-carbon containing, you've got a molecule bound to something else, or maybe a molecule bound to 2 things. But with carbon, we can get these huge organic, so organic basically means with carbon. We can get these really divergent, different structures just based on what carbon's bound to, how many things it's bound to. So so this on the left-hand side here, these are the same thing. One's just a space-filling model, the other is a line structure. But we have carbons bound to a bunch of hydrogens. This is kind of a long linear structure. Here we have carbons bound to a bunch of alcohol groups. So of these, that left-hand side, put your hand up. Do you think that this is going to interact well with the polar solution? So if you put that thing in water, is it going to float to the top, or is it going to, so let's put hands in and think that it's going to float to the top of a solution. Okay, the other option is going to be mixes perfectly well with water. So let's get a lot of hands for this one. Who thinks that that's going to float to the top? Okay. We've got all carbons and hydrogens, very low difference in electronegativity. It's not going to interact with polar molecules. But this thing on the right, this is glucose. Do you think that's going to go into solution easily? We have a lot of oxygens and hydrogens. Those are polar. They'll interact with the waters. I can tell you that this very sugary drink that I'm drinking is a good example of sugar mixing well with water. We didn't put a whole lot of energy in here, and there's already a lot of sugar in that. But the basics of these compounds are still pretty simple. All we have here is carbon, hydrogen, and water, and we can form these really divergent structures. So that's probably not a bad point to about wrap it up. Once more, I want to say that if anyone isn't on my email list already, please come up and put your name on the page here. Take a look at the syllabus so that you guys can get the reading for next week. This is on that list that I shared with you guys, but the readings for next week are going to be chapters 4 and 5. Come in prepared for that so that we can start digging into macromolecules and membranes. But we're going to pick up right where we left off. We're thinking about what happens when you have membranes in water. What things are going to stay on one side or what things are going to go to the other. Thanks, guys.